Today we want to keep looking at vector spaces, basis, and coordinates, and this is why everything pretty much looks like Rn. So let's start off with a basis for a subspace of R3. Notice that my basis has two vectors in it, B1 and B2. And so we're dealing with a two-dimensional subspace of R3. So to describe H geometrically, I want to, since H is a two-dimensional subspace of R3, H is a plane in R3 containing the origin. So geometrically, H is a plane in R3 containing the origin, because a subspace has to contain the zero vector. So H is a plane in R3 containing the origin. It's really important to note that H is a two-dimensional subspace of R3, but H is not equal to R2. Everything in H has to have 3 coordinates. Everything in R2 only gets to have 2 coordinates. So we want to note that H is isomorphic to R2, but it is not equal to R2. H is isomorphic to R2. But not equal to R2. So isomorphic just means that there is a one-to-one onto map from H to R2. So since it's one-to-one and onto, it is an invertible map. We can take the coordinates and map them to R2, and any coordinate, any vector in R2 will correspond to exactly one vector in H. But we don't want to say H equals R2. So the next part of the game is I can give you a vector and ask you for its coordinates, or I can give you the coordinates and ask for the vector. So in the first case, x is 4, -6, 6, and I want the coordinates of x relative to this basis. So what we want to do is we want to write x as a linear combination of b1 and b2. So this first question is to write x as a linear combination of b1 and b2. So that's what that question is about. That's what finding the coordinates of x relative to b means. Write x as a linear combination of b1 and b2. That is, we want to solve x1 b1 plus x2 b2 equals, I should not have used x, c1 b1 plus c2 b2 is equal to x. So I want to solve this vector equation. And then to do that, we're going to go set the Wayback Machine to the first week of class, and we're going to set up an augmented matrix with b1, b2, and x. So we're going to look at 1, -3, 5, 2, 0, -4, and then I'll put x as the rightmost column, 4, -6, 6. Since I only have 2 vectors in my basis, and I can see that it's a basis because one of the vectors is not a multiple of the other. We only get to say that when there are 2. If there were 3 vectors, I would have to make sure that those 3 vectors have a pivot in the matrix with those 3 vectors as columns has a pivot in every column. But it's really easy to see when there's only 2. B2 is not a multiple of B1, so they're linearly independent. So that means the reducer echelon form will have a 1, 0, 0 and a 0, 1, 0. Once again, the reducer echelon form shows us where the pivots are, but the pivots were always there. And then we just have to find the reduced echelon form, which it looks like I have done. So it's 1, 2, 4, -3, 0, -6, 5, -4, 6. So it looks like x1 is 2 and x2 is 1. 2, 1, 0. Oh, sorry, not x2. C1 is 2 and C2 is equal to 1. So here are the coordinates of x relative to b. Notice that there's only a C1 and a C2. There's 3 columns in my matrix, but this is an augmented matrix, so the variables only show up in the first 2 columns. I've got a C1 column and a C2 column. C1 column and a C2 column. So the coordinates of x relative to b are 2, 1. What this means is that if I take 2 times b1 plus 1 times b2, that should get to x. That should get me x back. So if I take 2 times the vector 1, -3, 5, plus 1 times the vector 2, 0, -4, I get 2 plus 2, -6 plus 0, and 10 minus 4. So I get 4, -6, 6. So this checks out. So here we are checking that these coordinates, this linear combination of b1 and b2, will get us x. 2b1 plus 1b2 is equal to x. 2b1 plus 1b2 is equal to x. So this checks out. We can also note that even though I checked with a vector equation, because I originally formulated the problem as a vector equation, we also know that if we multiply b coordinates by the standard coordinates of the b vectors, that will give us the standard coordinates. So I can reframe this vector, this linear combination, as a vector, a matrix multiplication. So if I write the matrix b1, b2, and I multiply by b coordinates of x, that will give me the standard coordinates of x. So if I take 1, -3, 5, 2, 0, -4, and multiply that by the b coordinates of x, which are 2, 1, we get 4, -6, 6. We don't really have to check this multiplication because it's the multiplication that we did up here. It's just a matrix form of this linear combination. Standard coordinates of the b vectors multiplied by b coordinates of x gives us standard coordinates of x. In the third part of this problem, we're given the b coordinates of a vector y. Notice that there's only 2 of them. We got a -3 and a -2, and we want to find y. So to get the standard coordinates of y, I just have to make the -3, -2 combination of the b1 and b2 vectors. So what this means, so since the the b coordinates of y are -3, -2. What that means is that y is -3 times b1 minus 2 times b2. Or I could frame this as a matrix multiplication. I could say the matrix b1 times b1 and b2 multiplied by the b coordinates of y will give us the standard coordinates of y. So all we have to do is that we just take the b1 and b2. I want to do it as a matrix multiplication, a vector equation first. So I'll take -3 times b1 which I can't remember, 1 -3, 5, minus 2 times b2, which is 2, 0, -4. So I'll have -3 minus 4, 9 plus 0, and -15 plus 8. So it looks like y is -7, 9, -7. We could also do this in the equivalent matrix way by multiplying the matrix with the standard coordinates of the b vectors by the b coordinates of y. And this is the same calculation that we just did. So what we want to notice is that the vector y is a vector in R3 and has to have 3 coordinates. But since we're looking at a 2-dimensional subspace of R3, the coordinates of y relative to b is in R2. That vector only has 2 coordinates because we only have 2 basis vectors. So it's really important when you're looking at a problem to know where the things you're working with, where those things live. In this case, y is in R3, but the coordinates of y relative to b are in R2. Let's make sure that we're very aware of where things are by changing this problem up just a little bit. So let's let, I need a different basis. I'll call it basis script P. So let's suppose that we have a basis for subspace K of P2. That is, K is the span of P1 and P2. And now I got to tell you what P1 and P2 are. Now, since we're dealing with P2, we're now dealing with a polynomial space. Now our vectors in P2 are polynomials of degree at most 2. So let's say P1 of t is, let me come up with something completely at random. Let's call it 1 minus 3t plus 5t squared. And let's say P2 of t, another completely random polynomial with nothing to do with anything that we've done today. Let's go with 2 minus 4t squared. So you may have noticed that I cleverly copied the first problem, but instead of R3, we're dealing with P2, which we know is isomorphic to R3 because coordinates and bases make everything look like Rn. So in this case, the vectors in P2 should look like polynomials, but the coordinates will look like vectors in R2. There are 2 vectors in a basis, so the coordinates are a unique linear combination of those vectors in the basis. But the vectors themselves need to look like polynomials. So for example, if the coordinates of y relative to b are -3, -2, the y that we're looking for now is going to be a polynomial. We can just use the stuff that we've had before. The standard coordinates of y, since this is just a copy of the previous problem, but in polynomial form, the standard coordinates of y will be -7, 9, -7. But in this case, since we're dealing with a polynomial, so if the coordinates are -7, 9, -7, I'm dealing with the polynomial -7 plus 9t minus 7t squared. In this problem, the vectors are polynomials, but the coordinates always come from Rn. We can run this problem. If we didn't have this problem to work with, we can still run this problem just like a polynomial problem. When I say the coordinates of y relative to b are -3, -2, that means y is just -3 times p1 minus 2 times p2. So y is -3p1 minus 2p2. So that's -3 times p1 minus 2 times p2. And then if we just use the distributive property and gather like terms, I've got -3 minus 4, +9 plus 0, -15 plus 8. Like I said before, bases and coordinates make every vector space look like Rn. Plus 9t. So the plus 9t is we've got -7, the standard coordinates for P2, or the standard basis for P2 is 1t and t squared. Oh, and it should be plus 9t. Now I see what it was. Thank you. All right, let's pause the video here, see if we have any questions on making everything look like Rn.